So this is a hardware conference, right? Is there any software people in here? Okay. I don't want to hurt your feelings, but no, I saw this was a hardware conference, and I came and I was looking at the board, and I was like, where's NVIDIA? And I thought, all right, they're a software company, so they're not here. And I just wanted to talk a little bit about hardware, because if you read the news, you know, it's ChatGPT and Llama and blah, 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 blah. It's all software, 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 software. And AI software is going to change the world. And so first, I just wanted to say hardware is beautiful. And I've been doing this for, yay, we got some cheers. There we go. Go eat, yeah, instead, like, so there's a wafer full of GPUs, I think, from AMD, which is a beautiful thing. And then there's gate-around transistors. And as people know, I believe Moore's law is not dead. You know, every once in a while it slows down and people working on it give up. But like, there's a lot of evidence it's going to keep going for a while. And you know, they ran out of drive strength on regular transistors, so we made FINs. And then we're making gate-around, and the way they make them is so insane, it'll just knock you out. It's a beautiful thing. There's a Tenstorrent box. We put 32 AI processors in 4U box, which finally works. I'm going to talk a little bit about that. And then the most badass thing there is Cerebras said, AI needs more transistors, so they made it really big. And I'm kind of like that kid on the playground, hoping somebody will jump off the roof to see what will happen. I'm a fan. It's a big jump. We'll see what happens. So hardware is beautiful, and there's so many pictures. I searched for hardware, and I found this really cool cooler, like water-cooled cooler for chips, and I walked in there to first table. They have water-cooled coolers, and I took pictures of those because I might use one. I thought it was great. But hardware is super cool, and more particularly, hardware, Moore's Law, God love him, is what has enabled AI. And there was a Jeff Dean quote years ago. He said, they got some AI models running on a single processor, and they did a whole bunch of work to parallelize it on 64 processors because they thought that would be better. And then they realized they were 1,000,000 times too slow, like 1,000,000 times, right? And for the people who believe Moore's Law is dead, I've been hearing about that Moore's Law for about 30 years, and it's been dead in about 10 to 15 for 30 years. And I don't think it is. But what happens is, as we get more transistors, it enables the next generation to compute. And a friend of mine, Pushkar, around a day, made this chart, and he said, oh, the Apple M2 is right on the line. And it just keeps on going. So this is a beautiful thing. So hardware, transistor count, enabled AI, and then AI models get published, and they look like this. And again, this is where I'm a hardware guy. So I look at this, and what I see is a pipeline of operations, right? Is that what it looks like? Has anybody ever seen a new model that wasn't published like this? So the programmers will tell you it's PyTorch or Python or CUDA or this or that or anything, but actually the thought process is it's a pipeline of operations. And if you notice, the operations hardly have any feedback, which is a beautiful thing. It has feed forward, which, by the way, is a super pain in the ass. But so AI models look like this. And there's lots of models, and they all look like graphs, right? I'm looking at the timer, and it says 25. Oh, it's counting down. Okay, great. I had to get synced up there because I'm used to dealing with more digits in a timer as of seconds. All right, we used to use nanoseconds. So AI models are expressed as graphs. There's a really high diversity of graphs. There's also a very high diversity of size of the objects, size of the data flow. And if you look at the number of operations in a graph, you think this can't be that hard, but then there's 50 startups working on it, and most of them can't do it. Sometimes us, we've had a lot of problems getting this to work. And so we're working on it. And there's something very attractive about graphs from a hardware point of view. So hardware designers love to make things go faster. We pipeline them. We allocate work to cycles. We build arrays of things, and our big toolkit is basically pipelines and arrays. Right, lots of transistors, shrink them down, build pipelines and arrays. And, and I talk to software people writing the code, because the code they want to write looks really simple, right? If you ever looked at a matrix multiply program, Andre Karpathy, has anybody heard of Andre? He's a real programmer. He doesn't care how the hardware works. He does care how the software works, and he wrote a llama model recently in C. And the inner loop of it is accumulator plus equals A times B. Like, could that have been simpler? Like, what's the big deal? Now, the index to one of those things has 3 parameters, including a multiplication, but that's the way the arrays are indexed. But there's a whole bunch of stuff that's kind of wild. So the programmers are thinking one thing, and the hardware guys are thinking another things. And that's partly because hardware people tend to be somewhat literal, and if you publish a graph, I think it's a graph, and then I go build hardware that optimizes the graph. So here's an example here of the brain did it pretty good. So the brain is really wild. So if people don't know, it's 10 billion neurons organized as cortical columns, and each cortical column is 6 layers deep, and between the layers, it's all-to-all computation. Now, all-to-all to me sounds like matrix multiply, because that's what they do, right? And each layer is doing a matrix multiply, and then the cortical columns talk to each other. And then you might wonder, why aren't the cortical columns bigger? Well, it turns out nerves have a really variable propagation speed. And in the cortical column, the propagation speed is very slow, and if it got bigger, it would have to speed up, which would raise the energy and screw up the speed-power product, which is super cool. The nerve that makes your finger move, when you say click, that moves a lot faster. It's way, way faster. The neurons are way bigger. They have special seats to enhance propagation. If people look, read this. This is the Wikipedia pictures. All right, so what we have here is an array of cortical columns, which are built as pipelines of computation. And then they have a cool property that cortical columns talk a lot to adjacent ones and less to further away ones. And beyond that, I have nothing to say about it, except it kind of looks like the computer I'm building. Computer designers love building pipelines and arrays, because that's what we're good at. I've literally been doing it for 40 years, and I still think it's great. And right. And the key is to make it go fast, you have to take the work, divide it into stages. And if the stages are too small, you have problems closing timing, you have all kinds of things. If they're too big, it doesn't work out. It's really great when you can replicate parts, that's great. There's a really interesting power curve. If your widget is too big, you have to drag all the bits across the whole thing. We see that in the brain, we see that in computers. If it's too small, they have to communicate too much, right? When you have to make lots of units, it's a shitload of design work. When you can make one thing and replicate it, it's really great, because you nail that one thing and you array it out. That's a genius. That's how we use 100 billion transistors. When I was a kid, we designed computers as digital with transistors. It was super fun. And somebody asked me, what's in your library? And I said, oh, we have both kinds of devices, P devices and N devices. We don't do that anymore. That was crazy. It worked pretty good for a while. So, okay. So I want to walk through a couple of examples of implementations and then talk a little bit about what we're doing and what's good and bad about it. So everybody's seen this picture. I just pulled this off a random Google search. So this is, I think, an NVIDIA GPU. And there's a really interesting thing about it. So they built chips with 6,000 to 10,000 thread engines, right? And then each engine, has to support multiple threads, because if you load your local memory and it misses, you have to wait for the data to come back. So then they have a lot of threads in flight. So if you look at and the reason they built this is because GPUs were built to run programs on pixels. And the screen has millions of pixels, and it's a genius thing. How many pixel processors can I get in a computer, right? But this doesn't look anything like a graph computer, right? You can run matrix multiply on it, but again, the genius of GPUs is you have a pixel engine that's independent. When you run a program on it, it doesn't talk to the other pixels. It's actually one of the rules of GPU programming. And so you can run the same program on many pixels, which is cool, but you don't really do all-to-all calculations all the time. It wasn't really designed for that. Now, it turned out because it has really good compute density, and with a set of libraries we call kernels, you can make this run really fast. But its standard mode of operation is read data from memory, process it locally per pixel, and then write it back. Right? So, and for a programmer, that feels familiar. It's called the load stored architecture. Data lives in memory, I read it in, I do some modifications on it, I write it back. That's cool, right? Now, if you want to read it in, do some processing, and give it to somebody else, well, you can figure it out. If you go read the NVIDIA instruction set and the recent updates, they're working on SM to SM communication, they have on-chip memory, but all those pieces are added onto an engine that fundamentally reads and writes memory, right? So you have two interesting things going on. You need a shitload of memory bandwidth because everything is reading and writing memory. And then the other is you have a lot of threads to coordinate on a relatively small number of objects, right? Which is, again, I showed you the graph. It's not complicated. There's only 10 things in it. There's not 10,000 things in it. Now, you have to be careful about that because over the last 5 years, the models have varied a lot. They started out very convolutional with lots of things. And then modern language models have very big matrix multiplies. One of the reasons is it's easier to program that kind of stuff. Now, your brain doesn't have big, huge cortical columns, right? So, as we evolve on AI and we search for power efficiency and effectiveness, I think we have to be very aware of how this computation is going to change over time. But very small threads doesn't seem a good match. So then TPUs, this is a V4 picture. They haven't sent me the V5 picture yet. I'm sure they will soon. But so TPUs started out with very large multipliers, which for the big language models running big arrays looks like a better fit, right? But the problem there is you in fact have lots of small objects. And now you have the problem of how do you pack all the small objects into a big matrix multiplier, right? Which takes it's a serious amount of work. And then it's essentially a VLW compiler. So now they have the VLW compiler problem, and I heard they had 500 people working on the compiler, which, was that true? Yeah. Oh, somebody just said, I was just checking. I come to conferences, ask a few questions, and then get some feedback. That's a wild number of people to work on a compiler, right? That says to me that the match between the hardware and the software isn't, there's some kind of mismatch there, right? And the history of computers is full of this, right? So, when we started making computers fast, it was single issue, and then the risk innovation was really simple pipeline, fetch, decode, register, read, execute, cache lookup, write back. And then as we made it faster, then we said, well, let's make that too wide. So now you have to put some instructions in there, and then we made it super pipelined. And then there was a big fork in the road. One was, we'll keep making the hardware simple but bigger and use a compiler to fix it. Or we'll build out-of-order execution engines. And there was a big school of thought that said, we'll never make out-of-order execution engines work. Right, and there's many people believe that. And they went down the VLIW route, and they quickly had teams of 500 people building compilers. Right, and it turns out that it didn't work. And there's a technical reason it doesn't work beyond the management problem. But that's a longer talk. And we did, in fact, figure out how to make out-of-order engines work. It was hard. But, at Digital, we built an out-of-order engine way back when in '98. And the core team to build the out-of-order engine was like 10 people. And the alpha compiler team was 70. And Intel was making Itanium. Their engine team was bigger, but that's Intel. Their compiler team was 500. And our chip was faster. So you have to think about this problem carefully. Okay. So Tenstorrent, being hardware guys, we have software people. You have to hire, you build hardware, you have to hire software. It's like a deal with the devil. It's like, it's nothing, like I've been doing it for a long time. I I feel okay about it. I've come to terms, right? But we looked at the problems and we said, we want to build arrays of processors optimized for the operations in the graph. And it turns out there are matrix multiply, convolution, vector operations, and a variety of data moves and transformations, right? We have local memory and DRAM to hold weights. You would really love to keep everything on chip, but the way the models are written and the ratio, let's say, of the sizes of compute to memory, you essentially need DRAM. And everybody builds a machine without DRAM regrets it. That's a problem. We have direct processor-to-processor communication, right? That lets data flow through the graph, because sometimes if you could keep the weights either local or schedule the weights streaming from DRAM to the local memory, the activations just slide right through the computer, right? And then we write software to transform the AI graph onto the hardware, right? Now here's a picture. So our next generation chip, we have about 200 AI processors. So compared to TPUs, it's big. Compared to NVIDIA, it's a small number, right? And there's a optimization point around you want the math engines to be big enough that they do useful work without too much communication. And it turns out in matrix multiply, there's a little term which is you do n cubed operations for n squared data, right? So as it gets bigger, the ratio of compute to data improves. If you make it too big, which would be very good for communication, then you're dragging all the data across the arrays. And then what people do is then internally it looks big, but inside it's subsetted, right? Which turns out to be the same thing, kind of. We added some RISC-V CPUs on the side of this because some graphs, the operations are C programs, and some graphs, the operations are math, which is cool. And then if you take a graph, for example, block 1 was a bunch of C programs, and 2 was some AI computation, and 3, our compiler takes that graph, breaks it down, and then shards big operations on the multiple processors to do that. Does that make sense? So this is a computer that looks like the problem, at least the problem as stated by everybody who's ever published an AI program. Now, when they talk, the programmers talk about it in the language of programming, but what they publish as a spec looks like, look, graph. And I'm saying that partly because some of my software friends will find that controversial, and then I can go debate them on Twitter or something. It would be funny. Okay. So the way we actually build the processor is kind of interesting. So you want a big matrix multiplier, you want a vector engine, you want a local SRAM, right? And then you need routers to the fabric, both to talk to memory and to talk to adjacent processors. And then we take a program and divide it up across those processors, right? And this is the somewhat novel thing. So when programmers do stuff, they load data from memory into a register, do operations on the registers, maybe test it, maybe not, right? And then they store it back somewhere. So if you run that thread in a CPU, soon as you miss and you wait for data, you stall, right? So what NVIDIA does is they have a large number of threads. So what they did is each guy has that load, math, store program in it, and every time they're waiting for something, they stall, and they switch threads. So we did it the other way. We said, put all the get data from other processors in memory in the first processor, put all the data that reads it from the local memory and transforms it into the register file in the second processor, put all the math in the third one, put the reverse transformations in the fourth one, and put all the programs that move data to other processors in the fifth one. And basically, they run asynchronously. Instead of having hundreds of threads per thread engine and thousands or tens of thousands of threads on the chip, we have 5 threads per Tensor core that each one runs until it's blocked. So the guy reading from memory doesn't use the data coming back from memory. It's just launching those operations. And the guy that takes the memory from the local guy and say does a compress or a pivot or data modification, there's a whole bunch of operations. Like the programmers are always changing the array sizes and changing the format, and so we do that as a thing. And then there's math. Math tends to run easiest, it turns out, because you say, oh, do a 100 by 100 matrix multiply. It takes a couple of clocks. So that's not very busy. And then the same thing happens on the output. Cool. So again, our mission is to build fast, efficient computers. And there's a couple things to say. There's a power efficiency advantage on making the arrays the right size. And there's a memory bandwidth advantage of being able to flow through data through the computer whenever possible without having to read and write memory all the time. So one of our things is we want to be competitive with GDDR6 memories with an HBM machine because we don't have to read and write all the intermediate data all the time. We want to flow the data through the machine. And then it turns out the numbers are kind of crazy. So HBM, everybody's talking, you need HBM. It's really expensive, right? The package is really expensive. The memory is really expensive. It costs something like 6 to 8 times as much to build a computer with HBM as regular DRAM, right? So you could have more compute, but you're spending money on DRAM, and we don't think that's the best answer. So, okay, so how do we do this kind of thing? So we have a compiler we call Buddha, and its mission in life, so you write PyTorch, TensorFlow, Onyx or something. We use TVM to make an intermediate graph, right? And then we lower that graph into our format and do some graph modifications. And then we modify it several passes to take big matrix multiply and make it into the right size for the processors you have. And then do the data buffer allocation, and then lay it out across the chip. So we have a place and route step. Again, hardware guys here, place and route. You take a graph with a lot of objects, you lay it out across a bunch of chips. And then it turns out the models are super variant in size. So we have an IP customer who's using like eight of these processors, and we have a machine in the lab with 100 processors with 100 chips in them, so it's 10,000 processors. And the compiler kind of scales from a couple of cores up currently to about 10,000, which is a pretty big range. And then the operates range from a couple of operates fit on a Tensor core, that's 5 teraflops. Does anyone remember when 5 teraflops was a big number? 1998, I was working with Cray, and they said their mission was a teraflop per megawatt. Now, to be fair, that was 32-bit float, and they had a lot of high memory bandwidth, and energy was cheaper, right? So now we talk about, we need 10 tops per watt. And so it's moved, and those tops are little baby tops, but it's moved about 100,000 to 1 million X in terms of power per operation. Okay, so we built a graph compiler, and one of the mistakes we made was we wanted this graph compiler to not only solve all graphs, but also do it performantly in all situations, right? And that turned out to be really hard, and it forced us to rewrite this compiler several times. But now we have a pretty good graph compiler, but we added a piece to it, or 2 pieces. So one is we made a set of tools we call Metal, which is if you know what you want, you know what kernel you want, you know the buffer size, you know all the pieces, you can define those pieces and put them right on the hardware and lay it out yourself. So this is more work to do. It's a little more like the CUDA kind of environment where you say, I'm going to program to the hardware, which is commonly called a Metal stack. And then we divide the compute kernels up. So when you write the program, you write it as one program, but there's part labeled reader, which is that pull the data in, and then there's the compute part, and then there's the writer, which pushes the data out. And then we have some standard semantics about local buffers, circular buffers, streaming buffers, so that when you write a program like this, you don't have to reinvent all the infrastructure for it. But if you know what you want, you can lay it out pretty good. So we have existing kernels, we have a kernel compiler. You sort of have to place the kernels in data, but the kernels we write are what's called scalable kernels, so they work from one processor to an array of many processors. So when you're writing the code, it looks like a matrix multiply call, but you define how many cores they are and possibly where it goes, depending on the state of the tool chain in the day. So this lets you lay out hardware the way you want, or software on the machine the way you want, and then if you want to push the performance to the limit, this is the way to do it. And if you want to make any old model run, you use the other compiler. So, and then we built a box we call Galaxy, which is 32 chips in it. And one of the transformer models is kind of cool because you build this object, and once you place and route it, it turns out it fits on one of our chips. We have a bunch of different versions of this. Then you can stamp out as many of these as you want, right? And they just data flow through it. When we first started building this computer, we thought we'd have this 32 by 32 chip grid. You know, it would look more like a brain. But all the models look like a long snake, right? They go through it. But actually it's not true. Each layer inside the chip is actually really big. So this model looks like it's a snake of 24 chips long, but in each side is this model, which is not that many layers, and each set of operations is huge, right? Now the cool thing about this is, again, versus HBM, the more chips you have, the more aggregate total memory bandwidth you have, right? And you can use all the bandwidth for that model. It's not like you have an 8-chip box and an 8-chip box and an 8-chip box, all doing the same thing and then, say, exchanging weights. That's bad for two reasons. In the box, you read and write memory all the time. All the things are training on, say, different pieces of data, so they all have the whole model in them, so they don't get the memory bandwidth with all the chips. And then they have to exchange the weights over expensive InfiniBand. Right. So we're different in a couple of ways. So our mission is, like, I love HBM, it's great. Per power per bit, bandwidth is super cool, but until we get the price sorted out, you can't get the low-cost, affordable AI with technology like that. You can't get there with InfiniBand currently, so we use 100 gigabit Ethernet, and we build a machine so multiple chips talk to each other, so we don't typically go through a switch. That's a very high bandwidth and expensive. We stream the data in parallel through lots of chips. We built matrix multiply units that are not too big, they're not too small. We think that gives us a power efficiency. And then the final point is, you know, as a business, we're willing to license both the CPU technology we built and the AI technology we built. Because it turns out the diversity of products is super high. You know, there's automotive, edge, video implementations, which is a relatively small number of cores. People want to build AI into the pipeline of, say, network data or video streaming data. It's a really interesting phenomena. So we're not going to build all those products. So we're building AI products, and we're starting to onboard customers. But, you know, our mission is to go solve the problem as stated in a way that's super cost effective and available to as many people. So, all right, so there's my assertion. AI models are graphs. Hardware guys love to work on graphs and pipeline them and make them go faster and turn them into arrays, and right. And the key when you build hardware is to match the software with the operations they say they want to use, which is clearly stated in all their definitions. We are now building both a top-down compiler, so you can take a high-level PyTorch program, elaborate it into graph with software, and get it to run, and a bottoms-up method so you can get your hands dirty if that's what you're into. And we think this gives a fundamental advantage and a path to lower cost, both on power and cost for AI. So, cool. I got 1 minute left for questions if anybody has one. There's one over there.
Hi, Jim. Great talk. In terms of cost, would you change your mind if HBM got rid of the interposer? So HBM on organic substrate, for example?
Maybe. Depends on the price. So here's the coolest thing. It took me a while to realize this. Consumer GPUs, those guys spent billions of dollars on technology. GPU packages are great and cheap. GDR DRAMs are great and cheap because it's a big market for something that needs to be commodity priced. Whether or not they're going to lower the price just because it's easier, I have no idea. So I know I've talked to lots of people about using organic substrates, you know, building chip carriers, chiplets. There's a whole bunch of cool things. And you know, whether that translates into lower costs, I don't know. LPDDR6X is also very good on cost per bit and bandwidth, but it's more bits at lower cost, but less bandwidth per millimeter or shoreline. So there's some interesting trade-offs coming. We'll see what happens. Yes.
Hey, Jim, what do you think about data formats? We've talked talked about FP8 earlier today. Where do you stand on different types of data?
I'm agnostic. We support 32, several 16s, 8, 4, and I'd be happy to do 2 and 1. Data formats don't matter. That comes from the definition of the algorithms, and then from a hardware point of view, you need to talk to people and go, are they really going to go to a smaller data format? There's also block formats. There's some really interesting stuff about how precision and exponents are managed. I think there's some really cool stuff there. We built our stuff so that we have basically a data formatter on the input and then the output of our engine, because lots of people say, well, this layer needs more precision, this one doesn't. And that makes the kernels composable, because you can write a kernel that's data format agnostic and then change the formats reasonably, and then the compiler needs to know a little bit about the size of the objects, because the size can frequently change. But yeah, that seems like there's some real efficiency on that path. Cool. Any question over here? That's you, yes.
So with the aggregated memory, does that mean that you now don't have to have a network connection for every GPU?
No, it actually means we do. Well, so we build a box of computers that are all hooked together with Ethernet, which we use as layer 2 transport. So a packet goes across our NAC, and we put a header on it, and we squirt it across. We don't use Ethernet as Ethernet. But somewhere that computer has real network attachment or PCI Express attachment to some host, right? And that runs a higher level protocol. So yeah, you could have 100 chips with, let's say, 16 of them talking to hosts. And that's just for parallel bandwidth. And it really depends.
It's similar to what they're doing with LLMs today, though, right?
Yeah, like LLMs in inference mode, you send it a sentence, you get a sentence back. So it's, a petaflop of compute per, byte of input. It's a pretty good ratio. You could run this thing on a SPI port.
But for training, though,
Training is a different thing. But then the question is, how big can you make the model to spread the weights and computation around and do the minimal amount of weight exchanging through expensive networking?
that was my question, really, was around training.
Yes.
So it's still a real one.
It's still a real problem. And there's a whole bunch of research to do on this, because I'm pretty sure our brain doesn't train. Does everybody realize this? This is the funniest thing. You start training with complicated things, you end training with complicated things, and it's all incremental changes. No human has ever learned that way. We start with really simple things, but as you learn, you make quantitative leaps. And the human data rate for training is really low. We do a maximum of 10 million inferences a year. It's really interesting. So I promise you training is going to change. It doesn't make any sense training a computer for 3 months on the internet with infinitesimal edits to weights. No human being has ever learned anything that way. It's not a thing.
Excellent. Well, thanks, Jim.
All set?
That is awesome. And we now know that everything is a graph. So
Everything is a graph. Hardware guys make graphs go fast.
yep.
Yay, hardware.
All right. Good
All
job.
right, we got